So this time what we're going to do is find the linearization of a function near a value a equals 0. So basically why we call this linearization or linear approximation of a function is it's the equation of the tangent line essentially. So what we have is we have a point A, and near there we want to say within some interval or near, whatever near means, we get that an equation of a straight line is exactly equal to or approximately equal to the values at A. They're exactly equal to the value of the tangent line. And so what we do is we define the linearization as the equation of that tangent line. So what we have is, how do we get the equation of this? From the picture, what we have is we have a point A, f of A, and at that value they're exactly equal to each other. And so near that value they're approximately equal to each other is the idea. So we have a point A, f of A, and we know from calculus now that the slope at that point is equal to the derivative at that point. Using the point slope form of a line, given a point and a slope, that is always the tangent line is equal to y minus y1 times m, which is f prime of a, x minus a. So this is the equation of the tangent line. I've moved this to the other side, and this is exactly the definition of linearization. F prime of a, x minus a, plus f of a. Linearization is the equation of the tangent line to the curve at that point. So now that we've sort of seen what linearization is, again, you can look at the tutorial videos for the gory details of what linearization at a point is and what differentials are. But basically the pieces I need to create the linearization is I need the a value, then I need f at a. The idea is we need an a value where I can actually compute in the function and the derivative. So when I put 0 in there, I get the square root of the third root of 1, which is 1. So I can compute this. So I need f of a. We know a is 0. I need f of a, which is f of 0, which is something that will be readily computable for our function. This is 1 plus 0, which is the third root of 1, which is 1. So something I can actually compute. And then I also need the derivative. So now we're going to have to use I really don't like the fact that it's written like this, so this is actually 1 plus x to the 1/3. When you're computing derivatives, you should be getting rid of nth roots. They're fractional exponents. So once I have this, I take the derivative of this, which gives me 1/3, 1 plus x to the negative 2/3 minus 1, technically by the chain rule times 1. If there's a 2 or something there, it'll get you. So I do that just by reflex, just to make sure. So this is 1 over 3 x plus 1 to the 2/3. Again, I need a value where I can compute my derivative at that value so we can approximate everywhere else. So f prime of 0 is equal to 1 over 3, the third root of 0 plus 1 squared, or the 2/3 exponent, which is equal to 1/3. So these are the pieces I need to put into the machinery. Now the linearization, remember, is just the equation of the tangent line to the curve at that point. Once I have all the pieces, LAX, not the airport in Los Angeles, the linearization of the function f at a is equal to f prime of a times x minus a plus f of a. For ours, I see what I've done for myself and what I've tried to train myself, and hopefully you over time, is when I use horrible definitions that I have to memorize, it's not a good idea to try and memorize those things. Instead, I keep reiterating them for myself every time I need them. There's the general definition of linearization. Then I put my values in with the example. Then L0 of x is equal to f prime of x, we computed, was 1/3, x minus 0, plus f of 0, which was 1. Cleaning that up, we can see that the linearization Lx of 0 is equal to 1/3 x plus 1. It should be the equation of y equals mx plus b because it's a straight line and it is the equation of the tangent line to the curve at 0. We can then use this to approximate like the third root of 0.99.